Complete proof system for one-free regular expressions modulo bisimilarity. I'm Clemens Grabner from the Gran Sasso Science Institute in L'Aquila, Italy. Welcome to my talk about joint work together with Wan Fokkink from the Free University in Amsterdam, the Netherlands. There are basically three parts already visible in the title: a complete proof system, one-free regular expressions, and bisimilarity, which hints at process theory. I will explain these to you first, starting with one-free regular expressions. Then I will explain to you Milner's process interpretation, and in particular his axiomatization question from 1984 for a particular proof system. We will not solve that question, but we will obtain a strong partial result concerning one-free star expressions and a system that we call BBP, where the letters stand for Bergstra, Bethke and Ponce, three colleagues of ours from Amsterdam. I will show to you why the classical proof approach for completeness fails in the case of this system, and what new proof approach we choose instead, namely one that uses structure-constrained process graphs, and in particular a condition that we call the loop existence and elimination property in a layered flavor. I will explain to you the main lemmas of our completeness proof, and in particular the most crucial lemma is one that states the preservation of the structure property Lie under bisimulation collapse. I will then put together these lemmas in a dynamical way to show you the inner workings of our completeness proof. Regular expressions, as defined by Kleene in 1951, in an algebraic modern formulation, can be viewed as the following grammar. We have a constant 0, a constant 1, we have letters over an alphabet, we have the possibility to form sums, products, and Kleene star expressions. Copy, Elgot, and Wright in 1958 used for the first time unary Kleene star, which gave them the possibility to do away with the 1, because it then was definable by 0 star. However, with binary Kleene star, 1 is not definable in its absence, and that gives us the possibility to look at one-free star regular expressions by using Kleene's grammar but dropping the 1, using binary Kleene star. We will also speak of star expressions instead of regular expressions because we subject them to Milner's process semantics, and Milner used the term star expressions to disambiguate the use of regular expressions under his process semantics. He interpreted 0 as deadlock, 1 as the empty process, letters as atomic actions that terminate afterwards. He interpreted plus as alternative composition of processes. He interpreted product as sequential composition, and he interpreted star as unbounded iteration with the option to terminate before and after each iteration. Then Bergstra, Bethke and Ponce interpreted binary Kleene star as unbounded iteration of the left part, with the possibility to leave the iteration before and after each step and continue with the process interpretation of the right sub-expression. Let's look at an example. Here you see a one-free star expression and its associated process interpretation. It consists of an outermost binary iteration that starts with an A step but has an deadlocking exit which is not reflected in the chart. Then there is an inner binary iteration that starts with an A step, continues with a B step, or with a B step that is followed by an A step, back to where the iteration started, and always the option to take a C exit. This is the chart interpretation of this one-free star expression, and we use the term chart for finite process graph following Milner. Here you see a somewhat more complicated star expression and its associated process interpretation, which has an innermost binary iteration, and its part in the graph is drawn in red here. A binary iteration in the middle with associated blue part, and an outermost binary iteration with brown part as drawn here in this chart. And there is an A step from the start vertex, which is drawn by a brown arrow here and always, to the iterative part. Now these two charts are bisimilar, meaning there is a bisimulation between them, with the meaning of bisimulation being a binary relation between the vertices of the charts that relate the start vertices and that make it possible to mimic individual steps in one chart by individual steps of the other, such that the targets are again related. So these two charts have the same behavior with respect to the comparison notion bisimilarity. We indicate that these two regular expressions have bisimilar process interpretation by this symbol. Now, the process interpretation has different properties from the standard language interpretation. In standard language interpretation, it is the case that every finite state automaton can be described by a regular expression that has the same language. The analogous statement is not true for the process interpretation. Here you see two charts that are not bisimilar to the process interpretation of any regular expression, any star expression. Note in the chart on the left, there is here at the bottom a sync termination vertex, whereas in the chart on the right, there is no vertex that has immediate termination. We will come back to these charts in a minute. Fewer identities hold for bisimilarity under the process interpretation than for language equivalence. One can see this by looking at the complete axiomatization by Salomar of language equality and then highlight those identities that do not hold under the process interpretation. There is the axiom A5, left distributivity, which famously does not hold under the for bisimilarity, and there is the axiom A8, which would say that every process that is continued by deadlock is bisimilar to deadlock, which is not the case. So Milner dropped these two axioms, added the commutative analogon that is sound for deadlock, A8 prime, and obtained this system and asked whether this system is complete for bisimilarity of star expressions under the process interpretation. This is still an open problem, and we're not solving that, but instead we are adapting his system to one free star expression. First by highlighting the occurrences of one, and then either dropping the axiom in question, or if it was a unary Kleene star axiom, turning it into a binary Kleene star axiom without an occurrence of one. Also, the fixed point rule here at the bottom has lost its side condition. And now we show this system by Bergstra, Bethke and Ponce to be complete for the process interpretation of one free star expressions. Now, coming back to one of these non-expressible charts, it is possible to view every chart also as an equational specification by associating variables to the vertices and letting at every vertex the outgoing transitions determine an equation. Then the associated equational specification you see here on the right. This, however, is not solvable in Milner's system nor in BBP, meaning there is no vector of star expression that, substituted for the vector of variable, would lead to a vector of equations, all of which would be provable in Milnor's system. This is not the case, and Milnor already showed that. With that, I can now explain to you why Salomon's proof approach does not work in our case. Here you see two star expressions that are bisimilar and their chart interpretations. Now Salomon suggested to look at the product chart of these two, and you see it here on top. Now note that this chart is of the form of the non-expressible chart. So it's not possible to extract a solution here directly. Note that here the transitions are labeled different from the non-expressible chart. So a solution here exists, however, it cannot be extracted directly. If it could, then one would be also able to extract a solution from the non-expressible chart. So this is not possible here, so we have to look for a different way, and one way would be to go downward instead of upwards and go downward to the bisimulation collapse. Here it's easy to extract a regular expression from it in this example, and the question remains, can a solution always be extracted directly from the bisimulation collapse? That is not clear from the outset. However, we will show that this is the case by using a property, Lie, a graph property that holds for chart interpretation and that is preserved under the bisimulation collapse. In order to explain that property to you, I first have to explain to you what a loop chart is. A loop chart is a chart with three properties. First, there is an infinite path from the start vertex. Second, every infinite path from the start vertex returns to it. And third, termination is not possible in the chart. If we look at this chart, then it's not a loop chart. There is an infinite path, but there is also an infinite path which gets lost in it and which does not return to the start vertex. So L2 does not hold here. Also, for this first non-expressible chart, it's not a loop chart, because although there are infinite paths, and all infinite paths return to the start vertex, termination is possible, and that violates the condition L3. If in the first chart we change the start vertex to the bottom vertex, then we obtain a loop chart. Here all three conditions are valid. The same holds if we change the start vertex to the middle vertex, then there is an infinite path, there are infinite paths, all infinite paths return to this new start vertex, and termination is nowhere possible. Then there is also the notion of a loop subchart. A loop subchart one gets by picking a new initial vertex and picking a number of outgoing transitions, here one, marked in dark blue, and then going further on path until the newly picked initial vertex is being met again. So this is a loop subchart. And now I can explain to you loop existence and elimination. Let's look at this chart. I have marked in boldface the entry transition of a loop subchart. This can be eliminated by just dropping it and performing garbage collection. Then we obtain this chart where I have already marked in boldface a next loop entry transition. This can be eliminated again, and then we obtain this chart without an infinite path. In the same chart, we could eliminate loop subcharts in a different way, in a first step, a second step, a third step, and then reaching this different chart that does not have an infinite path. Now the loop existence and elimination condition holds for a chart if and only if this chart transforms by a sequence of loop subcharts elimination to a chart C0 that is a normal form and that does not permit an infinite path. So the two non-expressible charts do not satisfy this property because they do not contain loop subcharts, but they permit infinite paths. However, the chart that we have just studied here on this last slide has the property Lie, because we have here already found two ways of loop subchart elimination procedure runs that lead to charts without infinite paths. We can now try to record such runs of the loop elimination procedure on the chart itself by using labels that show which loop entry transitions have been eliminated at what stage by using natural number labels. And in doing so, we can do that for all runs of the loop elimination procedure. What we obtain are so-called Lie witnesses, so witnesses of the fact that the loop elimination procedure witnesses the property Lie. These also have a layered flavor that, for which we give a formal definition in our paper and which is sufficient for the purposes of our paper. Charts that have a Lie witness we call Lie charts. With this notion, I can now explain to you the lemmas, the statement of the lemmas of our completeness proof. The first and most important one is that the bisimulation collapse of a Lie chart is again a Lie chart. We call a Lie chart is a chart that has a Lie witness. The second and the third lemma state that the chart interpretation of a one-free star expression E is a Lie chart, and it has a provable solution with start value E. We call that the provable solution is a vector of expressions, one for each vertex, and the start vertex, the start value of a provable solution would be the start vertex value of this vector. And then there are two more lemmas on this slide, namely that from every Lie chart it's possible to extract a provable solution. And the lemma SE, that all provable solutions of a Lie chart are provably equal. The last lemma I will explain to you in the completeness proof. The completeness theorem then states the following. The system BBP is sound and complete for bisimilarity of the process interpretation of one free star expression, meaning that equality of star expressions E1 and E2 is provable in BBP if and only E1 and E2 have bisimilar process interpretations. Now let's look at the proof of the completeness direction of this theorem. Let's assume that E1 and E2 are one free star expression with bisimilar chart interpretations. Then it is the case that these have the same bisimulation collapse. And importantly, there are functional bisimulations from C1, C of E1 and C of E2 to the bisimulation collapse C0. This will be important in a second. Now, the first lemma I said that for every one free star expression, the chart interpretation is a Lie chart. From that we can conclude that C of E1 has the property Lie and C of E2 is a Lie chart. Then we know that for every one free star expression E is the start value of a provable solution. So we can find that E1 is the start value of a solution of C of E1 and E2 is the start value of a solution of C of E2. Then we use the crucial lemma that the bisimulation collapse of a Lie chart is again a Lie chart, and we find that C0 is a Lie chart. Then we use the lemma E that for every Lie chart it's possible to extract a provable solution. So there is a solution E0, that's the start value of a solution of C0. And now a crucial lemma that allows one to pull back solutions conversely along functional bisimulations. So E0 is a solution, a start value of a solution of C of C0, I can pull it back to obtain that E0 is also a solution of C of E1, and E0 is also a solution of C of E2 at the start. And now we use that all provable solutions of Lie charts are provably equal. And from that we can conclude that E1 is provably equal to E of E0, and E1 and E2 is provably equal to E0 also. And now we can just use transitivity to show that E1 and E2 are provably equal. This is the proof of the completeness direction, because we started from the assumption that E1 and E2 had bisimilar process interpretation, and we showed that E1 and E2 are provably equal in BBP. Now, to give you an idea of the proof of the main lemma, that the bisimulation collapse of a Lie chart is again a Lie chart. What we do here is that we do not go to the bisimulation collapse in one step, but we choose a vertex-wise, point-wise collapse procedure that preserves the property Lie. So here in this example, you see a Lie witness, and in it two bisimilar points, V0 and V0 double prime. What we are now doing is we are sending all incoming transitions at V0 over to V0 double prime. So V0 does not have any incoming errors except the arrow that indicates the start, which then is sent over to V0 double prime, which gets the new start vertex. And the part with V0 is being garbage collected because it's unreachable. Then we are here in a situation that we have other bisimilar vertex, V1 and V1 prime. We are here in a situation that V1 prime loops back in two stages to V1. What is happening here is that we send all incoming transitions at V1 over to V1 accent. There is only one here marked in red, which gets also a loop entry label and is here marked in red. This is a transformation of the kind 2 that we use. And in the last step, we have another pair of distinct bisimilar vertices, namely V0 triple accent and V0 double accent, and they are here at, again, different positions for which we have devised a third transformation, which sends through all incoming vertices at V0 double prime over to V0 triple prime. And this chart that we obtain here is actually isomorphic to one that you've already seen before, which is a bisimulation collapse. So our proof proceeds with vertex-wise collapse steps that preserve the property Lie. And importantly, we show that there are three kinds of transformations, and we show importantly that if a chart is not a bisimulation collapse, then it always contains a pair of distinct bisimilar vertices to which one of these three transformations is applicable. This lemma has an important corollary, namely that a chart is expressible by a one-free star expression modulo bisimilarity if and only if its bisimulation collapse is a Lie chart. This is a polynomial decidable property. Now let me summarize. We have obtained a partial solution for Milnor's problem by adapting Milnor's proof system to one-free star expressions, finding a system that's already defined before by Bergstra, Bethke and Ponce. We have used a graph property Lie that guarantees solvability via extraction, holds for chart interpretations of 1 free star expressions, and is preserved under the bisimulation collapse. This we use to show completeness of BBP. Now the important question, would that be also possible to use for Milnor system? Well, perhaps, but that's not clear from the outset, because two properties, I and C, do not hold for all star expressions. So you see here a chart, which is the chart interpretation of a star expression with 1 and unary Kleene star, which is a bisimulation collapse but does not satisfy the property Lie. So in order to deal with that, a workaround has to be invented, and a suggestion that I've recently made on in an extended abstract for the term graph workshop is to use one chart, to use charts with explicit one steps. And I want to refer you for this further going idea to this extended abstract, and I also want to refer you to the report version of our article where the full proofs of our transformations and all of the lemmas that I've shown you can be found. So with this I want to end, and thank you for having me, and thank you for your attention.